So now that we've mastered the concept of within sample or alpha diversity, let's discuss beta diversity analysis, which is between sample diversity analysis. And for me, that's where the really interesting data lies, where you can relate your samples to one another, specifically in terms of factors of interest to your study. So where we're looking at the dog microbiome, that would be the treatment effect and the dog. And we'll see how that affects our beta diversity analysis. So to calculate beta diversity analysis, we'll do pairwise dissimilarity calculations. So between each pair of samples in your matrix, you'll get a beta diversity estimate. So for instance, dog 1 versus 10 and dog 1 versus all other dogs. And that gives us an estimate of how close these samples are to one another. And to visualize that, we would plot an ordination. So this dissimilarity matrix would then be used in a plot such as this. And here we can see we have for each point as one sample, and now we can clearly see how the different dogs relate to each other and also in terms of treatment. So here we can already see that dog K, which is the squares, samples irrespective of treatment are more similar to each other, and we can say the same for dog G, which is the little triangles, that irrespective of treatments they still are more similar to each other than between dog diversity. So we often speak about ordination in 16S analysis, and this is a term that's used in ecology to refer to several multivariate techniques for visualization of species abundance in low dimensional space. So you want to take that high dimensional data you have and you want to summarize it as easily as possible, hopefully in 2 dimensions, so you can see it on a plot such as this. So you can think of ordination as positioning samples in a space of reduced dimensionality while preserving their distance relationships as well as possible. So there are several beta diversity metrics, and a suitable distance metric specifically for 16S data or ecological data should consider certain factors. We mentioned that 16S data is compositional, so we have a lot of zero values in our matrix, and ideally we should consider abundance as well as composition, and then we can also consider phylogenetic relatedness. So often in previous analyses that are not 16S, you may have come across Euclidean distance that's commonly used for other data types, and you may think, why is that not appropriate for 16S type of analyses? And if you follow this link, there's a nice overview of why that's not ideal for this type of data analyses. So if you're comparing 2 samples, you might see that certain species are absent in both those samples, and in a nutshell, if we use Euclidean distance, this would make these 2 samples look more similar, even though that may not be the case just because they have an absence of both of those ASVs. So instead, we often use something called Bray-Curtis dissimilarity. And to calculate Bray-Curtis, that computation involves summing the absolute differences between the counts, which you see at the top here, and dividing this by the sum of the abundances in the 2 samples that you're comparing that pairwise distance for. So if we look at an example here, we have 2 samples, S29 and S30, and they've got 5 different taxa. So in this case, we would calculate for each of these comparisons for taxon A between these 2 samples, the absolute difference, and the same for B, C, D, and E, and that we divide by the sum counts for these 2 taxa across all samples, and that gives us our dissimilarity index. There's a second dissimilarity metric that is commonly used called unifrac distance, and the major difference between Bray-Curtis and unifrac is that unifrac incorporates phylogenetic relatedness. So to use unifrac, you actually need to import a phylogenetic tree in that phyloseq object that we made, and then there are 2 types of unifrac distance. normal or plain unifrac and then weighted unifrac, which in addition to phylogeny also accounts for abundance. So it's a quantitative measure, whereas unifrac on its own is a qualitative measure. So to calculate unifrac distance, if we look at the comparison here, just to give you an idea of when we have samples that are closely related versus ones that are less similar, if circles and squares denote different samples, we can see that branches attached to nodes that are colored black are unique to a particular environment or sample, and gray if they are shared. And in A, you can see the tree representing phylogenetically similar communities, where a significant fraction of that branch length in the tree is shaded gray. Whereas in B, we see two communities that are maximally different. So 100% of their branch lengths are unique to either the circle or the square samples. So we see now that there are different metrics we can use to calculate our pairwise dissimilarity matrices between samples. And there are also different ordination methods that we can use to visualize these pairwise differences. So one method that's really common for ecological data specifically is called multidimensional scaling, which is also known as principal coordinates analysis. So not to be confused with principal components analysis, which you may be familiar with. And actually, if you look at the mathematics, PCA can be seen as the simplest case of MDS, where the dissimilarity metric is Euclidean distance. But as we've discussed, Euclidean distance is not really appropriate for ecological data specifically. So what we will use is a distance metric like Bray-Curtis with our multidimensional scaling. And this will provide a set of uncorrelated or orthogonal axes to summarize variability in our data. So in MDS, the axes that we see on the plot will represent the proportion of variation explained by that ordination. Ideally, a successful PCOA should generate few axes, so 2 to 3, with a relatively large eigenvalue, so that should capture more than 50% of the variation in our input data. So we won't always have ideal situations like this, but it's good to keep in mind what your proportion of explained variation is, so you can judge the quality of your ordination. Then another option that is commonly used with 16S data is called non-metric multidimensional scaling. So this is actually an iterative method, so non-metric, where the raw dissimilarity values are converted into ranks. So here we use a random start seed, so it's an iterative process. So you should record that random start seed, otherwise you'll have a slightly different result every time. And what NMDS does is to locate samples in n-dimensional space so that your Euclidean distance, so on the plot, between samples corresponds closely to your actual compositional dissimilarity matrix that you calculated with Bray-Curtis or Unifrac or whatever. So to judge the quality of our NMDS, we can look at the stress value, and that's a measure of fit between your ordination and your input dissimilarity. So lower stress values are better, and as a ballpark we can use 0.1 as a minimum acceptable stress value. So when you get to 0.2, 0.3, you know it's not really a good representation of your input data. And sometimes that iterative process won't converge at all. So now the question is, when do you use MDS and when do you use NMDS? And for that, you can do some additional reading here if you follow this link. But basically, I like to do both of them on my data and see how much they differ. Ideally, they should look similar. You know, you want to see the same kind of patterns between MDS and NMDS. But in general, NMDS performs better than MDS if MDS requires 3 or more dimensions to represent your main distance relationship among sites. So NMDS is able to kind of squeeze or distort your ordination into 2 dimensions, and that is often useful for publication purposes. So in that case, you might prefer NMDS over MDS. So now that we've discussed the theory behind beta diversity analysis, we can switch back to our RStudio, R script, the dog microbiome tutorial, and get some hands-on experience. So what we're going to look at is this m.std phyloseq object. So the counts have been normalized across samples, so we can compare samples. And we briefly pointed out that if we look at our taxonomy for this data set, you'll find several ASVs like ASV 1, 2, 5, 6 that have the same species level annotation. So when we do our beta diversity analysis, it's better to collapse them down so that ASV 1, 2, 5, 6, and so on that have the same species level annotation get summed together as one unit. Because if we don't do that and we use Bray-Curtis distance, those ASVs will get seen as entirely different entities, even though they actually belong to the same species. So to get a more biologically relevant view, we're going to use this tax_glom function, and that you can find in the microbiome customs tutorial script. All that does is it will sum ASVs that have the same taxonomic level of annotation. So for instance, 1, 2, 5, 6, and so on, together into one unit. Say there was an ASV that only had genus level ID to Clostridium, then those ones again will get summed together. So we keep the maximum amount of taxonomy that we have. So you can run that, and you'll see while it's running that, it'll remove your phylogenetic tree, because it's summing the ASVs together. If you did have a phylogenetic tree, that is no longer relevant to this data because you're now losing some of your ASV IDs. And you can ignore those warnings, and it tells us that we now have 124 merged taxa. So if we look, for instance, at the taxonomy table now, for the new phyloseq object, so that's m.phi, and then those ASVs have now been summed. So the next thing we want to do is to filter out taxa that are only present in a very low number of our samples. So in this case, we're going to filter OTUs that are present, so we want them to have at least 10 counts and at least 20% of samples, or we want them to have total relative abundance of at least 0.1% of the total number of reads. So that just eliminates spurious ASVs that maybe is present in one sample at low numbers, and we're not really interested in looking at those downstream. So for this we use the filter taxa function, and you can find that in the phyloseq package. So you can look at the help there, and basically what we're giving it is a phyloseq object as the first argument, and then we're giving it a function to filter by for the second argument. And we can use true or false depending on whether we want to keep or let those ASVs go. Basically what we're saying here is we want at least 10 counts in more than 20% the length of X, so that is your total number of samples, or we want the counts to be more than 0.1% of the total relative abundance. And we can apply that filter, and you'll see that leaves you with 106 of your initial 124 taxa. So in the next video, we're going to continue and actually use this filtered object to do our beta diversity analysis.